Okay, so today we're gonna do a very common integral, and this one has a more general format. So we have ik is from 0 to infinity 1 plus x to the power of k dx, where k belongs to the reals and k is greater than 1. So let's go ahead and finish this one first. So let's set u is equal to xk over 1 plus x to the power of k. Well, this one is also 1 minus this baby. And this thing right here is this, just saying. Du is equal to 1 plus x to the power of k, kxk minus 1, minus xk, kxk minus 1. Whoops, that was not enough space. So let's move that over. Thank you. Over 1 plus x to the power of k dx. And du is also that's also a square. So we have kx k minus 1 1 plus x to the power of k squared dx. We don't know what x to the power of k minus 1 is, so we have the following function. Xk is equal to u times 1 plus x to the power of k, which means xk is u over obviously 1 minus u is that fraction on the right, so 1 minus u, and I think that one is just flipped over. So we have u over 1 minus u. So x to the power of k minus 1 is just u 1 minus u of k minus 1 over k. So now we know, obviously, we need to find dx. So dx is 1 plus x to the power of k squared, obviously, and then 1 over k xk minus 1 du, which means this one, well, this one I think is just 1 minus u squared. So we have 1 over k, 1 over 1 minus u squared, and then we have 1 minus u over u to the power of k minus 1 over k du, which means this is 1 over u to the power of that's 1 minus so let me think about it. K minus 1 over k is negative 1 over k plus 1, and then we have 1 minus u to the power of k minus 1 over k minus 2 du. And let's write one more step to say that this is that's just 1 minus, so we have this du. And now we could start subbing in things. Let's do the boundaries also. When x is 0, that just implies u is equal to 0. That one's quite obvious. And when x is infinity, we use the expression on the right, and then we know that u is equal to 1. Now, with all that calculation out of the way, we have from 0 to 1, that's 1 minus u. Yeah, that is definitely 1 minus u. And then we have whatever monstrosity that is down there, that is dx. So we have 1 over k, oops, excuse me there, and then that's 1 over u, negative 1 over k plus 1, and then we have 1 minus u, negative 1 over k minus 1, du, which means we have 1 over k, and then flipping that, we have u 1 over k minus 1, and then we have 1 minus u of 1 minus 1 over k minus 1 du, and which means this looks like the beta distribution. So let's go ahead and do that for k, and then from 0 to 1. Oops, excuse me there. U 1 over k minus 1, 1 minus u, 1 minus 1 over k minus 1. And then we have the beta thing, du. This one is a probability density, distribution function, not density function. And this is integrated through omega. So this thing will be 1. And then beta of that is just a bunch of gammas multiplied. So we have gamma 1 over k, gamma 1 minus 1 over k, and then we have gamma 1 over k plus 1 minus 1 over k to the power of negative 1. This one, gamma 1, is just 1. Oops, excuse me there. Gamma 1 is just 1, so we could ignore that. So we have 1 over k, and then gamma times 1 over k, and then with multiplied by this gamma function, we have this property. So we'd have sine pi over k on the bottom of pi, and that's it for this generalization. So when we want to find I4, it's really straightforward. We could just say this is 1 over 4 pi over sine pi over 4, and sine pi over 4 is root 2 over 2 times 4 is just 2 root 2, so we could conclude that this is the case. And this is the easiest way out, because we could just use the beta distribution. The other way out is to use partial fractions, but that will take absolutely 75 million business days, so I'm not going to use that method, and I'll end the video here.